Alright, so let us now continue our discussion. In the previous video, we proved theorem 641, which is about a linear operator on a finite dimensional vector space having all its characteristic roots in the underlying field. And then what was the conclusion? The conclusion was that the space then has a basis in which the matrix of the operator is triangular. And at that time, we also said that this theorem has a matrix version. Whatever result you state for an operator algebra has a similar result for the corresponding matrix algebra, because these two algebras are isomorphic. And the similar result for matrices need not, of course, be proved because of this isomorphism. It already follows from theorem 641. So let us now see its matrix version. In original theorem 641, we had an operator. In its place, now we will have a matrix. In the original one, we had this operator algebra. Now we have this matrix algebra, Fn, of all n by n matrices whose entries are coming from F. And A is one such matrix. And just like that operator, that statement, here also A has all its characteristic roots in F. Then there exists an invertible matrix C in Fn such that CA C inverse is a triangular matrix. Alright. Now there is one more result in this section, which is this one. This result is also about such operators which have all their characteristic roots in the base field F itself. But unlike theorem 641, this time we are going to conclude something else. Now we are concluding that then T satisfies a polynomial of degree n over F. And in fact, in proving this, we are in the beginning itself, we are going to use theorem 641, namely that V has a basis on whose vectors T acts in a triangular manner. So we will start with that. So let's now start the proof. I can start from there also. I mean, at least I can write one sentence. Since T has all its characteristic roots in F, it follows from theorem 641 that V has a basis consisting of n vectors, of course, because V is n dimensional, such that for some reason I can't close the curly bracket nicely here, such that V1T is, we should write alpha 1 1 V1, but let us write lambda 1 V1. We will do something with these special coefficients. Okay, that's why we are writing them differently. V2T is alpha 2 1 V1 plus lambda 2 V2. and then let me write the general one, VIT. VIT is alpha I1 V1 plus alpha I2 V2 plus alpha I minus 1 Vi minus 1 plus lambda I Vi. See, this is one drawback of writing double subscripts like this. I mean 1, 1, 2, 1. When you have to write things like this, you have to use a comma. This is simply to separate I from I minus 1, so that we do not confuse I minus 1 for I square minus 1. No, it's not that. For all I from 1 to n. Okay. Equivalently, now what we will do, we will subtract these last vectors from both sides of this equation. In other words, we are now going to write V1t minus lambda 1 V1, which can also be written like this. So you are applying the linear operator t minus lambda 1 on the vector V1. By definition, this is V1t minus lambda 1 V1. Oh, by the way, because we have written t minus lambda 1, what is the actual meaning of t minus lambda 1? You cannot, of course, subtract simply a scalar from a linear operator. It really means this, where this 1 is the identity operator that does not change any vector. Then when you apply this on V, then say I am applying this on some vector V. We get this first, and then this becomes V1. And when you apply the identity operator on V, you get V back. So you get Vt minus lambda 1 V. So that is why V1t minus lambda 1 V1 is that thing. Okay. There is no need to keep this. It will look ugly, coming in the way of this system of equations. And then what we do with the second one, from both sides of the second equation, we are going to subtract the last vector lambda to V2. That will give us similarly V2 times t minus lambda 2, but this time we won't get 0 because we will have this alpha 21 V1. And if we do this with the general equation, subtracting from both sides lambda I Vi, then we are going to get, and this time we will have many things. I1 V1 plus alpha I2 V2 all the way up to alpha I minus 1 V I minus 1. Okay, this also, all these things for all these values of I from 1 to n. Okay. Now note that t minus lambda 1, when you apply this operator on V1, you get 0. Applying t minus lambda 2 on V2 does not necessarily give you 0. It will become 0 if alpha 21 is 0. That, however, is a condition. I mean, it's not always 0, but something else is always 0. Something else is there which if you apply on V2 an operator, then you will always get 0, and that is this. Note that on V2, instead of simply applying t minus lambda 2, we are next going to apply this. We can multiply these two operators. Why? Because in the operator algebra, there is a multiplication of operators, right? And that's why it's an algebra instead of simply being a vector space. What is that multiplication? If you recall, that multiplication is nothing but function composition. So here we are looking at function composition. Now if you calculate this, what will happen? First you will apply t minus lambda 2 on V2. So that will give you this. Alpha 21 V1, on which you have to then apply t minus lambda 1. Because t minus lambda 1 after all is a linear operator, so it will respect scalar multiplication. So this will become this. However, this thing is 0, and that's why we are ultimately going to get 0. Let us do one more step. Also, this time let us apply t minus lambda 3, t minus lambda 2 and t minus lambda 1, their product on V3. First of all, be careful with V3, okay. On V3, if I write this next equation here, then it will become more clear. Let me write it. T minus lambda 3 will be alpha 21, alpha 31 plus alpha 32 V2. Okay. So that we will have for this. Alpha 31 V1 plus alpha 32 V2. On that we are applying this product of t minus lambda 2 and t minus lambda 1. Okay, now what are we going to get? See, this product itself is a linear operator, and we are applying that on a linear combination of two vectors V1 and V2. So it will distribute itself over the linear combination. Because it's a linear operator, it respects both addition and scalar multiplication. So we are going to get alpha 31 V1, on which we are applying t minus lambda 2 times t minus lambda 1. So this is one of the vectors plus alpha 32 V2, on that also we apply the same operator. Okay. Now we don't immediately know what the t minus lambda 2 image of V1 is. However, we do not need to know, because we can change the order here. bring t minus lambda 1 first in front of this and push t minus lambda 2 to that side, plus what is this? This is 0. Okay, so we have already got one of the vectors 0. So this will vanish. But what about this? This one is 0. Let me still write 0. Okay. Actually, it's really advisable to go through all the steps when doing such calculations. Why is this 0? Why is this the 0 vector? Because we know from the theory of vector spaces that when you multiply the 0 vector by any scalar, you get the 0 vector. That's why. Then we get this. Plus 0, of course, need not be written again. What has happened here? We have applied the linear operator t minus lambda 2 on 0. And that gives us 0. Why? Because linear operators do that. That's because a linear operator, after all, is a group homomorphism. Of what group? Namely, the additive group of the underlying vector space V. And you are applying that group homomorphism on the group identity 0. So that will give you the identity again. Okay, and because of a similar reason, this is again 0. So you see that you keep getting 0. The only thing is that you have to start from t minus lambda I if you have Vi here. And in fact, similarly, t minus lambda I, t minus lambda I minus 1, like that, all the way up to t minus lambda 1 is equal to 0, and in fact this is true for all I from 1 to n. However, one thing is still not clear. Is this justified that we have switched the order here? Yes, this is justified. Any two such operators commute. But exactly why? Well, you just simply think like this. You take t minus alpha and t minus beta, where alpha and beta are scalars. Calculate this. Calculate this means what? Perform the multiplication. Because you are in an algebra, so using all the algebra rules, you can multiply out the terms. You do similar thing for this. You will see that the two results agree. That's why you can change the order you can write any such product in any manner you want. Thus, if, okay, now you note one thing. You see, first of all, what we did, we applied simply t minus lambda 1 on V1. That itself gave us 0. But we had to apply t minus lambda 2 times t minus lambda 1 on V2 to get 0. Alright. Now, if instead of applying t minus lambda 1 on V1, if you would have applied this on V1, then then also you will get 0 because you can change the order, bring t minus lambda 1 here, push t minus lambda 2 over there, and that would have also given you 0. For V3, this was 0, right? Now, if you apply this product on V1 as well as V2, you are going to get 0. In other words, the more terms we are including in this product of operators, the more we can apply that final product on these vectors and get 0. In that way, if you finally consider thus if S is this linear operator, which is the product of all such t minus lambda i's, then if you apply this operator on any vi, you are going to get 0. However, the way we have written it is not exactly the way we were following in writing these products. We have started with lambda 1, but again, because you can any two such terms commute, so this is actually also equal to this. I mean, if you continue this pattern, finally you are going to get this. Then applying S on any Vi will get you 0. Okay. However, these are not ordinary vectors. These are basis vectors for our vector space V. In other words, any vector of our vector space is going to be a linear combination of these Vi's. Now, because S vanishes on every such Vi, so S is going to vanish at every vector of the vector space. In other words, S is actually the 0 transformation. So we write, since this is a basis for V, we have Vs equal to 0 for all V belonging to capital V. In other words, the operator S is actually the 0 operator. But then if S is the 0 operator, thus T satisfies the polynomial this x minus lambda 1, x minus lambda 2, x minus lambda n minus 1 times x minus lambda n. Because when you put t in place of x in this polynomial, you get s, which is 0, over f of degree n. It's obvious that this has degree n. You can apply the degree formula since it's a product of n linear polynomials, each of which has degree 1. So its degree will be the sum of the degrees of those polynomials. There are n of them, so the degree is n. And that's what we wanted to prove. Okay, so we have proved in this section that if a linear operator on a finite dimensional vector space has all its characteristic roots in the base field, then it can be triangularized, and also it satisfies a polynomial over the base field of degree n. Unfortunately, this is not always the case, which means that the condition that all the characteristic roots of a linear operator be in the underlying field is not always true, which is why we cannot apply these results to such operators. One simple example, operators are matrices. One simple example of this condition not being true is this. You consider the 2 by 2 matrix. Is it what the hell I forgot? No, it's not a diagonal matrix. Okay. Yeah, it's this matrix. This 2 by 2 matrix with real entries. That means we are assuming this in the matrix algebra R2 of 2 by 2 real matrices. It turns out that this matrix has the minimal polynomial x square plus 1 over R. To verify how that is the case, you calculate this square plus the identity matrix. You are going to get 0. And no linear polynomial is satisfied by this matrix, which is non-trivial. No non-zero linear polynomial is satisfied by this matrix. And that's why this is an annihilating polynomial for the matrix, which annihilates, means makes the matrix 0 of least positive degree. That's why it's the minimal polynomial. It's monic also. But this polynomial has no root in R. Both its roots are non-real complex numbers. We know very well. One of them is I, the imaginary unit. The other one is minus I. So that's why what can we do? On this we cannot apply any of these results. In that case, the thing that we can do is, if R is not working, what do? You consider an extension of R, which in this case is C, the field of complex numbers. Say you have an n-dimensional vector space, say you have a vector space over F, a field such that the dimension of V over F is n. Okay. Now you have a linear operator T on V such that T does not have all its characteristic roots in F. Then what you do? You find an extension K of F which has all the characteristic roots. But then what are you going to do? Then you cannot exactly apply your these results on T, but you have to change the situation by embedding the original vector space into a larger vector space. Vk. over the extension field K such that the dimension of Vk over K is still n. Why exactly we need this? We don't need to understand that, because anyway we are not going to do whatever we are saying here. The author only says that it can be done. And one way of doing this is to consider a basis for V over F. Okay, and then consider the set of all formal symbols or formal linear combinations like this. However, these alpha i's will be coming from K. I say formal because you cannot exactly multiply V1 by alpha 1 if alpha 1 is coming from K, because these alpha i's may not lie in F, and we already have a scalar multiplication of elements of V by scalars coming from F, not from a larger field K. So that's why these symbols remain formal symbols, and then on Vk you apply an addition, a suitable scalar multiplication that will turn it into a vector space, and then you can embed V into Vk. In other words, you will find a suitable isomorphic copy of V inside of this, so that essentially V becomes a subspace of this, and then you proceed from there, whatever you want to do about this situation. However, then the author says that this entire construction depends heavily on our choice of this basis. We can see that clearly because we start with a basis, and then whatever we do depends on that basis. And this is not aesthetic. This is not really anything beautiful. A basis-free way also exists, which, however, involves the notion of tensor products of vector spaces. And for some reason, the author in this book has decided to not consider tensor products. Okay, that is why this is not an approach that we are going to take. So there is no real need to think about this. We are going to instead do something which will get the job done, but we will do it for matrices in this way. With matrices also we are going to have the same problem like this one. Not every matrix will have all its characteristic roots in the underlying field F. So this is how we are going to approach the problem. Consider the algebra Fn of n by n matrices whose entries are coming from F. Let K be any extension of F. Alright. Let T be an n by n matrix. Do not confuse this T with an operator, okay, because normally by T we mean an operator, but here for some reason the author has decided to take T as a matrix. So let T be an n by n matrix. Let Px be the minimal polynomial of T over F. Okay, so this means that Px is the lowest degree non-trivial polynomial over f that T satisfies. Now, note that since K is an extension of the field F, so Fn is a subalgebra of Kn. I mean, it's something very easy to see now. The n by n matrices that we have in Fn have their entries from where? From F, and because F is after all a subset of K, so those entries also lie in K, and that is why that n by n matrix also lies in Kn. So Fn is a subalgebra of Kn. Now because T is an element in Fn, so we also have T as an element of Kn. Now as an element of Kn, T will also have a minimal polynomial. However, this minimal polynomial will be a polynomial over K, and there is no necessity for this minimal polynomial to be exactly equal to this minimal polynomial, because this is a different algebra, no? Where the underlying field is also different. There are more elements, possibly more elements in K than we have in F, and that is why the entire situation may change. So you may have a different minimal polynomial for T over K. Let us give that also a name. Let P naught of x be the minimal polynomial of T over K. Alright, now watch this. What is Px? Px is an element in the algebra Fx, I mean the ring Fx. Since Px belongs to the polynomial ring Fx and Fx is a subring of Kx, we have Px also in Kx. Alright. Now Px is in Fx actually, but in particular it's also inside the larger Kx. And if you put T in place of x in Px, you get 0. Moreover, P of T is the 0 operator. In other words, Px is an annihilating polynomial for T over K, and P naught of x is an annihilating polynomial for T over K having smallest possible degree, because this is the minimal polynomial. That's why P naught of x has to divide Px. Hence, divides Px. And that is why whatever roots P naught of x will have will also be roots of Px. Now note that we did this for any extension of f. Now however, we are going to take a special extension of f. Let K now be the splitting field of Px. We know that such a field exists, and this we know from field theory, and the exact result is theorem 532. See theorem 532. Alright, so this is not any K but a rather special K. In this K, however, Px, because it's the splitting field of Px, it will contain all the roots of Px. And because we are mentioning splitting field, let's also recall what a splitting field is. If you are given a polynomial over some base field f, then that polynomial may not have all its roots in f. What do you then do? You then have extensions of f, which will have all the roots of Px. Among all such extensions, there is an extension of minimum possible degree over f. K is such an extension, and we know that it's unique also. So that is the splitting field. Then K has all the roots of Px consequently. K also has all the roots of P naught of x. Why? Because of this divisibility relation. Every root of P naught of x is also a root of P of x. P of x may have some other extra roots, but all the roots of Px lie in K, and all the roots of P naught are also roots of Px. So they also lie in K. And that's what we wanted, right? I mean, so now T belongs to Kn, T belonging to Kn is such that all the roots of its minimal polynomial P naught of x over K lie in K. And when that happens, we have that language of ours which says that, I mean, another way of saying this same thing is that all the characteristic roots of T lie in K. On this T, when you consider it as an element of Kn, you can apply all those results we have developed in this section. However, that is about Kn, not exactly about Fn. Sometimes, if we are lucky, looking at the result that we get for T considered as an element of Kn, we can go back to Fn and see that, okay, the same result actually is also true when you consider T to be an element of Fn, which it is actually, in truth. But that there is no guarantee that this will always happen. And finally, there is something else also. The author has defined about matrices. For any T in Fn, we say Now let me put it this way. By a characteristic root of T, we mean an element lambda in K. But what is K? Where K is the splitting field of Px. But then what is Px? Where Px is the minimal polynomial of T over F. Okay, so for all these things, we say that lambda in K is a characteristic root of T if the matrix T minus lambda is not invertible. That means it's a singular matrix, not a regular matrix. Well, actually we do not say singular matrix. I mean, we do say, but not in this stage. We have said so far. Regularity and singularity have been defined for operators. But of course, because matrices and operators are interchangeable, because the two algebras are isomorphic, so for matrices also you can say regular or singular. In place of regular, actually we use invertible. So this is not invertible as an element in Kn. When this happens, we say that lambda is a characteristic root of T. And when we say a characteristic root of a matrix T, this is what we mean by that. Okay, so and with this, the section is over. There are many exercises which we will solve in the next linear algebra update in the community section. And that's just it for tonight. So see you tomorrow with whatever comes next. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.